Okay, hello everybody. My name's Daniel Riley. This work on exact loop-bound analysis is done with Grigory Fedyukovich at Florida State University, where I'm from. All right, so first let me sort of set the stage here with what we're talking about with loop-bound analysis. Typically, loop-bound analysis aims to estimate how many iterations a loop in a program will perform. And if you have that estimation, this can be quite useful because you can then extrapolate to get some sort of idea of the cost of a loop in terms of energy, compute, memory, this kind of thing. And most studies are on upper and lower bounds. This has been applied to systems out in the wild and has been useful for program analysis with applications to worst case execution time, scheduling and resource allocation, complexity analysis, termination analysis, and then of course debugging. But we asked the question, what about exact bounds? So, as I said, there's extensive literature on upper and lower bounds. And usually in that literature, if any mention of exact bounds is made, it's in the context of when upper and lower bounds meet, so they're the same. But we thought, well, what if we dial this definition up to 11 and look for more precision for this exactness? So it could be that for any execution of a loop, there's different classes of executions that may have their own bound, and this isn't captured by an upper bound or a lower bound. And what we aim for is that an exact bound should give precisely how many iterations each class of execution of a loop performs. And so we also have the goal in this development that our exact loop-bound analysis should be generated statically and automatically. All right, so then let me describe what I mean by this exact loop-bound analysis, sort of the high-level idea here. So given a single loop program, we want to find a function that computes the exact number of loop iterations based on the input values of a program. So I have a small example here in a C-like program where we have two integer variables that are inputs to the program. We don't know what they are initially. And we have a single loop here that to enter depends on these two variables, both being greater than 0. If we enter the loop, then on each iteration, these variables are decremented. And to give you an idea of what an exact loop bound for this program should look like, it could be something like this, where, again, we're taking in those input values, y and z, from the main program. These are the inputs to the exact bound function. And here you'll see there are three cases for this particular program, this particular loop. One where the exact bound is just y number of iterations, another case where it could be z, and then for this loop, it's possible that you don't enter the loop at all, and so the loop won't iterate, will iterate 0 times. And you see this exact bound captures all three of those cases. Okay, so now let me sort of describe the construction of our problem here. So on the right here, I've shown the skeleton view of some augmentations that we make to an input program. So the first thing we do is we add a transition counter. This is a pretty common technique in bound analysis. And we initialize it to some value returned from a function f. Again, so this is like I showed on the last slide, where this function takes in the same input parameters as the main program. So initially, though, f is unknown. Inside the loop, we decrement our transition counter on each iteration. And what we're trying to do is find an f such that when the loop terminates, after the loop, our transition counter has exactly the value 0. So this is the assertion down at the bottom here. We say TC should be exactly 0. This brings a connection to safety verification, where for a good implementation of f, this assertion at the bottom of the program should hold after any execution of the loop. All right, so here's the example I showed earlier, but this time with the augmentations that I just described. We have our transition counter being assigned some value, return value of f that depends on y and z. We have tc, and we have our assertion. So realistically, what this f function should look like, it should be piecewise. We should have a piecewise construction to this function so that we capture all possible cases of the loop execution. The strategy then is to discover each piece of f separately. We want to look for a precondition that narrows down the set of executions that we're examining, and a so-called local bound that applies to that set of executions described by the precondition. All right, so first, although I listed it second, the first thing we do is look for a local bound. What we do is we perform like an angelic execution of the program. So this is just a symbolic execution where we're looking for some good thing, namely that our assertion holds at the end of this execution. We unroll the loop some finite number k times, and we use an SMT solver to get values for the variables in the loop at each step of the unrolling. And then from those values, we guess a local bound. But you'll probably say, well, this guess is not as precise as what you're looking for, and you're right. But we use this, it's good enough to classify a certain set of executions. So just to give you an idea of what this trace could look like, this unrolling that we do, we might start with initial values of y is 2, z is 3, and tc is 2. Then we go through the loop one time and another time and terminate. And we've gathered a set of data here for each step of this unrolling. And it kind of makes sense if you look at it, right? Because we see that tc is 0, which we said should hold after the loop. So we have that here. But we also have that y equals 0. So why does that make sense? Well, as you see, the loop depends on one of y or y and z being being greater than 0 to enter the loop. We have that. But then to terminate the loop, one of them needs to reach 0. And so this trace captures that behavior as well. All right, so now we need to relate these variables, namely to our transition counter. And a possible local bound for this example is simply that tc equals y initially. So at the top, our function f should return y in this case. But this is only part of the solution. When should f return the initial value of y to initialize tc? So we need to, this is where we get into our precondition synthesis for this particular case. And we use abduction to classify the bound. So again, we perform some sort of bounded unrolling, and then we perform several abduction. We perform abduction several times on these unrollings. So for an unrolling of length 1, we'll get this case here where initially y and z are greater than 0, but y equals 1 and z is greater than or equal to 2. We'll perform another unrolling and get another result. Perhaps we can do a third and get another result. And this is great, but it describes only particular cases, namely when we unroll 1, 2, or 3 times. So we need to generalize then on these results to get a precondition for our bound. In this case, we can generalize. The obvious bit is that y and z are greater than 0 initially, but the interesting bit is that for this particular bound to hold, we could find that z is greater than y. And then our transition counter should be assigned the value of y initially. So you and I could look at this and sort of squint our eyes at the program and say, okay, yeah, this looks good, but we want We want more guarantees than that. We need to verify that this guess at a bound is correct. So we perform another augmentation to our program with this new bit of information. So now we have the original augmented program where we have TC assigned to y this time, and above it we have the assumption, which is the precondition that we found. And then the rest of it is still the same with our assertion that TC equals 0 at the end. Then we send this program with the precondition assumed and TC assigned to y, and we look for an invariant to prove the safety of the augmented program. We can use any external tool for this safety check, and what we find is that this is a good solution. This program, with this restriction here that we restrict the number of states in the program to the ones described by the precondition, and then when we assign TC the value of y, we find that this assertion at the bottom of the program is not violated. So we've found a part of an exact bound for this program, but we're not done. As I said, there are some other cases here for this particular program. So the search continues. And we move to the next iteration of our exact bound search. So what we do is we take the precondition that we found in the first step, and to avoid a redundant search, we negate it and place it as an assumption at the top of our augmented program. Then we go through the steps again. We perform an angelic execution to get perform an unrolling to get some new data, guess a new bound, and then look for a precondition on the new bound. So when do we terminate? Well, we perform analysis at each step where we have a precondition and we want to look to see if we need to continue our search, and we terminate when the preconditions that we found do not allow entry into the loop. Here's a little display of the architecture of our exact loop bound analysis. So this just goes through the various steps. We unroll the augmented program. We look for a local bound, which we use an SMT solver. We unroll the original program. We look for a precondition on that unrolling, which also utilizes an SMT solver. We go to check safety and then check coverage. This is the check for the termination of the analysis. If we've explored all of the possible executions of the loop, we report an exact bound. If not, we continue through the analysis. All right, so we've implemented this idea into a fully automatic algorithm in a tool called Elba. It uses Z3 as the underlying SMT solver. And we've also implemented a sort of in-house data analysis tool to infer our variable relationships. We use Gauss-Jordan elimination and the equation of a line for this analysis. For our invariant generator, our safety checks, we use the tool Freecorn. And of course, we've performed some experiments to check how good this idea actually is. And what we found is that Elba can find 62 out of 75 single loop benchmarks. We find 62 exact bounds. These benchmarks including in the benchmarks from SVComp, and then others come from termination and bound analysis work. We compared against a few other tools. The upper bound solver Lupus and Coat, and then the termination analysis tool FreeTerm, which finds ranking functions to prove termination. We found that Elba finds exact bounds on the same order as these other tools come to a result for their own analysis. And then we looked a little further and said, okay, well, so the Lupus and FreeTerm Coat, they're looking for different things, but do they coincidentally come to an exact bound? And on 28 occasions, Lupus did, and freak term came to this result 10 times. But you can see that Elba is more than twice as good at finding exact bounds on this set of benchmarks. So we think that's pretty good. Our safety checks for Elba are quite fast in most cases, which is important because we perform several dozen of them at any iteration of our analysis. All right, so to summarize, I've talked about a new approach that we've come up with for exact bound analysis. It's a fully automatic and iterative solution. We generalize from a few inputs to many. We get correctness guarantees on the bounds that we generate from safety checks. We found 62 out of 75 single loop benchmarks on our experiments. And we have several ideas for future work here, which is to extend this approach to multiple loop programs. We want to apply this exact bound technique maybe to upper bound synthesis. Perhaps we can make an advancement here. And then we think that we can also return some information about partial bounds. There could be loops where some executions of the loop are non-terminating and others do have a terminating condition. So we think that we can apply our technique to discover this sort of thing. So that's the talk. Thank you very much for listening. No, the bound function should be loop free. Yes.
So just pick them else.
That's right. Yes.
If that's the case, it sounds like you can just take the off-the-shelf cytosolvers, run the loop with random inputs for any data, and collect all the data, and then run cytosolvers to generate the if then else expression. Have you ever tried that?
That's not something that we've tried. It's an interesting idea. I guess I'll have to give that some more thought. But the point here is that, well, and I guess I should have mentioned this, that we find that Elba performs this analysis very quickly, so sub 20 seconds. I would imagine that the approach you're describing could be quite intensive. But yeah, that's something that I would have to maybe give some more thought to. Sure.
Other question? First one on the right.
Hi. I was wondering how you would characterize the loops that you used for your evaluation. I guess I am convinced that this can find bounds for these kind of arithmetic loops like you showed. What I'm less convinced about is that you could find bounds for something like a linked list traversal where the iteration count is something like there exists an index into this list such that the item exists and the number of iterations is that index minus the start index. And I feel like I'm just curious if there's anything like that, a kind of data structure traversal that you've got in your evaluation.
No, so you're right. We have limited the scope for the loops that we apply this to. So we haven't gotten to linked lists, arrays, this kind of thing. There are a few conditions that we need. We need determinism in the loop, and that's what we. Yeah, so that's one of the main things is the determinism inside the loop that we need. I didn't talk about it in future work, but this is something that that we're looking into actually. Yeah.
Thank you.
Let us take the last question.
You mentioned at some point use of Gauss-Jordan elimination. Does this mean that all of your inferred bounds are linear in the program variables, or can you infer like nonlinear exact bounds?
Yeah, so another good question. So right now we're limited to Leah. So yes, linear relationships. We have some work towards nonlinear approaches. Funnily enough, so I mentioned Gauss-Jordan elimination. It's actually Gauss-Jordan's not very useful here. It's this canonical equation of a line relationship that is the most useful technique for finding the bounds for the programs that we analyze.